Okay, so today's topic of effective nuclear charge is the first periodic trend. And there's going to be 3 trends that we go over in this unit, and there's another one that we go over next unit. So, okay, now that you guys know what the Bohr diagram is, you have an idea that you have different energy levels, and these electrons are in these different energy levels. Right? So if we look at a very simple Bohr diagram, let's say there's an electron in energy level 1. Let's say there's 2 of them there. And then let's say there's an electron in energy level 2. Okay? And I'm going to draw another diagram similar but a little bit bigger. Okay, so here we've got energy level 1. There's 2 electrons. And energy level 2, I'm just going to say 8 electrons because I don't want to make it all messy if I draw all 8 in there. And then here we see an electron in energy level 3. Okay, so if I asked you what type of attraction, or which one of these two would attract its electrons more, do you think it would be the first or it would be the second? Second, maybe the second. What would the reason be if it was the second?
More mass in the nucleus?
More protons. Protons in the nucleus, okay. That's a possibility. There's also a case to be made for the first one as well, because the attraction that's taking place between the positive nucleus and the negative electrons, if I were to kind of zoom in a little bit. So the nucleus attracts the electrons here in energy level 2. The nucleus here attracts the energy levels in energy level 3. The nucleus has to reach through more levels to get through to attract that outermost electron. Does that make sense? Okay, it's kind of like think of these energy levels here as layers of insulation. All right, and the more layers of insulation there are, the harder it is for the nucleus to attract electrons. Whereas here, the electrons are so close to the nucleus, that's actually a little bit easier to attract them. So, let's define our first term. Effective nuclear charge is the net attraction that electrons feel from the nucleus. Now, both of these diagrams here, all of the electrons are attracted to the nucleus, but how strongly they're attracted can vary. And so we need to break this down and do this mathematically because that's going to be the most straightforward. So there's a formula for calculating effective nuclear charge. It is Z, which is the number of protons, right, minus S, and S stands for core electrons, the number of core electrons. So you remember that for any element, we can write out its SPA notation, and we can identify what are core electrons and what are valence electrons. Okay, so for example, lithium. The element lithium is atomic number 3, so it has 3 protons. The SPDF notation for lithium is 1s2, 2s1. Okay, so if I said, all right, which ones are core and which ones are valence electrons? Energy level 2 is the highest. So those are going to be my valence electrons. Or actually, there's only one there, so that's my valence electron. And then 1s2, those 2 electrons, that's what's considered the core. So Z minus S equals ENC. Z is 3, S is the core electrons, which is 2. The effective nuclear charge of lithium is 1. So what that means is, even though the nucleus of lithium has 3 protons, the electron in the valence shell actually only feels that there's 1 proton there because of the electrons that are in between the nucleus and the outermost electrons. Okay? So let's kind of see if we can identify a pattern. Let's do a couple more. All right, so boron, or no, beryllium. Beryllium's the next one here. So beryllium is element number 4, right? So the ANC for beryllium would be 4 minus, and so we've got to figure out what the core electrons are for beryllium. So off to the side, I'm just going to write beryllium as 1s2, 2s2. All right, so the energy level 2 is the highest energy level. Those are my valence electrons. And the 1s2 is underneath. That's my core. All right, or in other words, that's S. So 4 minus 2. And so the effective nuclear charge for beryllium is 2. And herein lies the importance of being able to determine the difference between valence electrons and core electrons. Okay? All right, let's do it for boron. Boron is 1s2, 2s2, 2p1. So those are my valence. These, again, are my core. All right, so the effective nuclear charge for boron has 5 protons. How many core electrons does boron have? 2. 2 again. So the effective nuclear charge is 3. So interesting. We went from lithium to beryllium to boron. Do you guys all see how they're in the same period? From left to right, lithium, beryllium, boron, right? And so the number of protons went up, but the number of core electrons did not. So I'm always in the same row. I'm always going to be subtracting the same number of core electrons. Let's do carbon just to be sure. So carbon is 1s2, 2s2, 2p2. Whoops, that's not a 2. 2. Okay, so carbon has 6 protons. I wrote P instead of 6. So 6 protons minus the 2 core electrons. So the effective nuclear charge of carbon is 4. All right, so quite clearly we are establishing a trend. What's the trend?
Going up by 1.
Yeah, effective nuclear charge goes up by 1 from left to right. Okay, so ENC increases from left to right. All right. So what about the other pattern, which is vertically? Let's talk about a vertical trend. Remember, what do we call elements that are in the same vertical column? Groups. They're the same group or same family. So we just did lithium. We saw that lithium was a +1. So the element below lithium is sodium. I'm going to make some space here. All right, so for sodium is 1s2, 2s2, 2p6, 3s1. So the effective nuclear charge for sodium which has 11 protons, how many core electrons does sodium have? 10, yes, good. So the effective nuclear charge of sodium is 1. Wait, sodium is in the same family as lithium. Lithium also had effective nuclear charge of 1. Okay. Let's do potassium. Potassium is also an alkali metal. So potassium, which is 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. Okay. The effective nuclear charge of potassium would be 19 protons minus how many core electrons in potassium? 18. All right. Well, I think this makes sense. If they are in the same column, they have the same effective nuclear charge. Okay? Same family equals same E and C. All right. So first of all, are you guys okay with finding the effective nuclear charge? You should write out the SPDF notation first, and then you take the protons, and from it you subtract the core electrons. Okay. And then you need to understand how the effective nuclear charge changes. From left to right, it increases by 1. But if it's in the same column, they're all going to be the same. All right, so let's look at a picture. So these are the S and P blocks on the periodic table. If I took a periodic table and I folded it, so like if we ignore the D block, then what you see is 8 columns. And that's what we're seeing here, okay? So this is a table of their atomic radius. Atomic radius, all right? So what we should notice is from left to right in a family, and this is the second period, what is happening? Emma, what's happening to the radius from left to right? It's getting smaller. All right, so it's getting smaller. Well, how did we define effective nuclear charge?
It increases.
No. How do we define it? Like the definition? The net attraction between the nucleus and electrons. So if the attraction increases from left to right, then the electrons are being attracted more strongly from left to right. And that is why the atomic radius gets smaller and smaller and smaller, because the effective nuclear charge is higher. All right, so atomic radius decreases left to right. Cause the effective nuclear charge increases, so electrons more strongly attracted, thus smaller atoms. And that is true in every period. Second period, third period, fourth period, doesn't matter which period. It's the same pattern. They get smaller. It gets smaller because the effective nuclear charge gets higher. All right. Now let's look at this vertically. What is happening to the radius in any family vertically? What's going on here? Allie, what's happening to the radius?
It's bigger as it goes down.
It's getting bigger. It is definitely getting bigger. So atomic radius increases from top to bottom. Okay, so let's think about what the cause of that would be. What did we say about effective nuclear charge in a family? Did the effective nuclear charge change from lithium to sodium to potassium? No, it didn't. So if that was constant, then that can't be the reason why the sizes are getting bigger as we go down. Nate?
The mass.
Sort of. Not so much the mass, but something is definitely increasing.
Protons.
That is increasing. Keep going.
Neutrons, electrons.
Electrons. And what happens when you have too many electrons where you filled up one energy level? You fill another one. And what happens when that one gets full? You fill another one. So this, in energy level 1, in period 1, there's only one energy level. In period 2, there are 2 energy levels. In period 3, there are 3, 4, 5, and 6. So very simply, the more energy levels there are, the bigger it's got to be. The more energy levels there are, the bigger it is. And that's true for every family. It doesn't matter if it's the first column, second column, seventh, or eighth column. Are we okay with that? So what this means then is I should be able to give you a pair of a pair of elements, and you should be able to tell me which one is larger or smaller. And you should be able to tell me the reason why. Okay, so let's hide that picture so it's not directly in front of you. I'm going to point to the periodic table. All right, how does the size of gallium, which is element 31, compare to the size of selenium, which is 34? Gallium and selenium. Which one's bigger? Ben? Gallium is bigger, yes, correct. Why?
Because it's farther to the left.
Oh.
The same energy level.
So it is in the same energy level, and it is farther to the left, but let's not use its position as the answer. The explanation has to use the vocab that we went over today. Then, Nate.
Gallium has less ENC. meaning
Yes.
that-
Gallium has, absolutely. Which means it attracts its electrons less, which is why gallium is bigger. Okay? Let's try another one. Selenium, 34, versus tellurium, 52. Which one is bigger? Selenium, tellurium. Yeah. Okay.
Tellurium is bigger because it has more electrons.
More electrons, but more accurately, another term is better than electrons.
More energy level.
Yes. Tellurium is bigger because it has one more energy level than selenium does. How are we doing? Okay? All right. Good. So that's actually as far as I wanted to get today in the notes.